Welcome students. In the last lecture, we discussed about the predicates as well as quantified statements and the negation of quantified statements. In today's lecture, we will discuss about multiple quantified statements and pre and post condition in design specification. Students, in today's lecture, our focus will be on how to decide the truth value for the multiple quantified statements and how to specify pre and post condition in, a, in the form of predicates in the design specification of software. The first kind of multiple quantified statements are where universal quantifier comes first, and then we have an existential quantifier with a certain property, and domain may be different for the universal quantifier and existential quantifier, and the domain may be the same. To show that such kind of statements are true, you need to show that for each and every element in set D, you can find at least one element in set E satisfying this property. Let us consider that section A of formal method is a domain D and section B of formal method course is domain E. Then for each and every student of section A, you can find a student in section B having the same age. If you can show this property, then that statement would be true. And you must be able to meet the following challenges to show the truth value of such kind of statements. Imagine that someone is allowed to choose any element whatsoever from the set D, and imagine that the person gives you that element, call it X. The challenge is for you is to find an element Y in domain E so that the person's X and your Y taken together satisfies the property or predicate Pxy. Now we consider the following examples, and these two examples are multiple quantified statements and having universal quantifier coming first, and there is existential quantifier. The domain for the universal quantifier is first 100 integers, positive integers from 1 to 100, and the domain for the existential quantifier is same, and you need to show that for each and every element in this domain, can you find an element in the second domain such that the square of the element in the first domain is equal to the element of the second domain. Yes, first you choose 1 and 1 square is equal to 1, it is okay. Then you will choose 2, 2 square is 4, yes, you can find 4 here, it is true. Then you will pick 3, 3 square 9, you can find 9 here, it is true. Then uh, comes 11, 11 square is 121, but you cannot find 121 here, therefore you cannot find this square of each and every element in the first domain, and you cannot find here in the second domain, therefore the first multiple quantified statement is false. Similarly, for each and every element uh, in the domain from 1 to 50, Can you find a value and whose sum is 3? Yes, you start from 1. For 1 you can find 2 here, and 1 plus 2 is equal to 3. Then 2 comes, 2 plus 1, 3, yes. Then 3 would come, 3 plus, but you cannot find any element because 3 plus 1 would be 4, and you cannot find uh, any element in the second domain for 3. Therefore, again, this multiple quantified statement is false. Students, now we have another kind of multiple quantified statement where the existential quantifier comes first, and then we have a universal quantifier with a certain property or a predicate. In order to understand the formation of such kind of multiple quantified statement, let us consider a domain of students in section D, and there is another domain of students in section E, and X represents uh, the CGP of a student in section D, and Y also represents a CGPA of a student in section E, and predicate is X greater than Y. And we have a statement that there exists a student in section D which has a CGPA greater than each and every student in section E. To show that this statement is true, you need to find at least one student in section D who has CGPA greater than each and every student in section E, then the statement would be true. Now we consider an example for the multiple quantifier statement where existential quantifier exists on the domain of first 1000 positive integers, and then we have a universal quantifier on first 100 positive integers, and the predicate is j is equal to I, and we need to pick an element from the first domain which is equal to each and every element of the second domain, and this is not possible, therefore this statement is false. Now we have another example containing three quantifiers, and uh, existential quantifier is on the domain on first 10 positive integers. Then we have a universal quantifier on first 10 positive integers. Then we have existential quantifier on first 200 positive integers, and a predicate is j square plus I is equal to k. uh, J is a variable declared on the domain on first 10 positive integers, and I is a variable declared on the first domain of 10 positive integers, and k is a variable declared on the last domain on first 200 positive integers. And we actually need to pick uh, an element from the first domain, and by adding this element to the square of each and every member of the second domain equal to a single member in the third domain. And if let consider I pick uh, 1 from the first domain, and 1 plus the square of 1 is 2, and you can find 2 from the third domain, and it is true. Now I pick again 1, and 1 is added to square of 2, which is equal to 5. You can find 5 here, therefore it satisfies the property. Similarly, I again pick 1 and I add 1 to the square of 3, which is 10. You can find 10. Similarly, I pick 1 and add it to the square of 10, which would be equal to 101. And yes, you can find 101 in this domain, therefore uh, satisfying all the elements of the second domain, and this statement is true. In order to conceive the idea of getting the truth value for the multiple quantified statements, let us consider an example. The first multiple quantified statement: for all triangles x, there is a square y such that x and y have the same color. In this multiple quantified statement, for all quantifier or universal quantifier is on the domain triangles, and there exist quantifier or existential quantifier is on the domain square, and we have a property that x and y have the same color. So for each triangle we need to find a square having same color. We start from the triangle D, and can you find a square having same color similar to D? Yes, square E has the same color as triangle D. Now we come to triangle F. Can you find a square having same color as triangle F? Yes, square G has the same color as F. Now comes triangle I. Can you find a square with the same color as I? Yes, same square G also has same color as triangle I. So we have considered all the triangles and we can find a square with the same color. Therefore, the truth value for the multiple quantified statement is true. Let us consider another example. There is a triangle X such that for all circles X is to the right of Y. Now existential quantifier is on the domain triangle, and for all or universal quantifier on the domain circles, and you need to find the property, or you need to satisfy the property that X is to the right of Y. So can you find a single triangle or at least one triangle which is to the right of all the circles? Yes, the triangle D is to the right of all the circles. Therefore, this multiple quantifier statement is also true. The solution of the examples given in the previous slide are also given in the form of a table. For the first multiple quantifier statement, where uh, a, uni a universal quantifier comes first, you can find the triangles. There were three triangles D, F, and I, and for D you can choose E, and for F or I you can choose H or I square having same color. Therefore, the first multiple quantifier statement was true, and the other multiple quantifier statement was where existential quantifier comes first. Therefore, you need to pick at least one triangle which is to the right of all the circles. Yes, D is also to the right of all the circles. Also, I is also to the right of all the circles. Therefore, the second multiple quantifier statement is also true. Students, the predicates beginning with two different quantifiers uh, have different semantics. For example, if you uh, changing the order of quantifier, their meaning as well as truth value may also be changed. Let us consider a multiple quantified statement. For all integers, there exists integer y where y is greater than x, which says that given any integer, we can find one bigger than that, and it is true. For example, we have integer 1, and you can find integer 2 which is bigger than that, and you can pick integer 2 and you can find bigger than that which is 3, and so on. Whichever value you will pick in the set integers, you can find bigger than that. Now consider another multiple quantifier statement, and we are swapping the quantifier. Now you can see that the existential quantifier comes first and universal quantifier comes after the existential quantifier. There exists y, and for all integer x, y is greater than x, and this says that we can find an integer that is bigger than all the integers, and it is false. You cannot find an integer which is greater than all the integers. Therefore, you can observe that by swapping the order of quantifiers, the meaning as well as the truth value has been changed. Students, software design represents an internal structure of a program. It also describes what the program components are and how they are related to each other. During system design, a functional specification is transformed into a system design. Such a design will consist of a series of discrete units, which are known as components or modules. And these modules contain procedures and functions which are related by virtue of tasks they perform. While formally specifying the software design, we actually call the procedures and functions as operations, and each operation may have preconditions or postcondition. Students, we have mentioned earlier that while specifying formally the functions and procedures of a program unit are known as operations, and each operation may have precondition and postcondition, and we can use predicates to describe these preconditions and postconditions with slight changes. Such specification will consist of two predicates, as I mentioned, which is known as precondition and postcondition. Precondition relates the values of global variables and parameters before a program unit is executed, and postcondition relates the values of global variables and parameters after a program unit has been executed. Students, we use natural language to specify procedures and functions, and we consider an example. A procedure sum up out has two parameters. The first parameter is an integer array value val, which has a range from positive integer 1 to integer 10. The second parameter is a boolean variable outRange. This is set true if any value in vals is less than or greater than 2000. To formally specify this procedure, we use a predicate which is given here. When the value of variable vals is less than 2000 or vals is greater than 2000, implies outRange is equal to true. In order to understand the formal specification of precondition and postcondition, let us consider another example. The function of the update procedure is to update the value of a global variable system state. The procedure has one integer parameter temp. It has post condition. If temp is greater or equal to 200, then system state is set to 0. Otherwise, system state is set to a value of 1. And the procedure has precondition. System state will have a value ranging between 0 and 5. Temp will range from 0 to 1000. Variable temp will be unaffected by the procedure. In order to formally specify the precondition, we have a predicate which is temp is greater than or equal to 0 and temp is less than or equal to 1000, which actually describe that range of temp from 0 to 1000, and system state is greater than or equal to 0 and system state is less than or equal to 5, which actually mention that when temp is range from 0 to 1000, then system state would be from 0 to 5. And we can formally specify its post condition that temp prime is equal to temp and temp is greater than or equal to 200 implies system state prime is equal to 0 and temp is less than 200 implies system state prime is equal to 1. Students, primes over the variable indicate the value of the variable after a program unit has been executed. Basically, we use a prime notation to describe the post condition value of the variable. Now we have another example. A procedure with the name update has two integer parameters. The function of the procedure is to examine its first parameter flag and set its second parameter value. If flag lies between 0 and 10, then value is set to 0. However, if flag doesn't lie between 0 and 10, then value is unchanged. Students, you need to write the corresponding post and precondition for the procedure update. Its answer is given here. The question says nothing about the values of the parameters flag and value on entry to procedure update. Therefore, no precondition can be constructed, and we can formally specify the post condition of the procedure, which is actually describe if flag lies between 0 and 10, then the value is set to 0. Therefore, flag is greater than equal to 0 and flag is less than equal to 10, which describe the range of flag between 0 to 10. Then the value of the procedure would be 0 and prime indicate the post condition value for the parameter value. Now we describe precondition and post condition of a procedure which need quantification to formally specify through predicates. The procedure add up has three parameters, array1, array2 and array3. All the parameters are integer arrays with range from 1 to 50. The function of add up is to add corresponding elements of array1 and array2 and place their sum in the corresponding element of array3. On entry to add up, all the elements of array3 will be 0. Because array3 is used to store the sum of the corresponding elements of first two arrays, therefore we describe the precondition as for all I of type on domain 1 to 50, array3 I is equal to 0. As you can see that Universal quantification is on the domain on positive integers from 1 to 50, and we actually uh, storing 0 to each corresponding elements of array 3, and its post condition would be for all I of type 1 to 50, array 3I is equal to array 2I plus array 1I. So the sum of corresponding elements of array 1 and array 2 is stored in the corresponding element of array 3, and we have described the predicate using universal quantifier over the domain on positive integers from 1 to 50. Students, in this lecture we described the multiple quantified statements, and we discussed a multiple quantified statement where universal quantifier comes first, and then we have existential quantifier. Then we discussed another type of multiple quantified statement where existential quantifier comes first, and then we have a universal quantifier. And we discussed that how to decide the truth value of the multiple quantified statements. And at the end of this lecture, we discussed that what are pre and post condition for procedure and how can we formally specify using predicates. Students, the contents of this lecture are taken from section number 3.3 of chapter 3 of the book Software Development with Z, and chapter 2 of the book Formal Software Development from VDM to Java. Students, you must read the contents which are mentioned in the slide, and that's all for today's lecture. Allah Hafiz.